Okay, let's start. Yeah, plan for today is not very clear because, to be honest, I haven't done my homework either. Has any of you done any homework? Made any MNIST or so? Ah, I see. Yeah, so we can do two. I haven't done it either, so I'm not even sure whether it will work as I think, but I'm optimistic. We can do two things today. We can either try to get this MNIST classifier, which has little to do with biology, but brings us a little bit of machine learning practice. The other thing that we can do is that we try to implement a simplified UMAP, which might actually work. In both cases, I give us about a 50% chance that we get something out that works, but if we all work together, maybe we can lift it a bit higher. Any preferences? Yeah. The MNIST? Okay, then let's try the MNIST. We did it last time with this bead. Where did I find this bead, this cluster we used last time? Where it was on Kit, right? Anybody remember which link this was? Jupyter Hub. Ah, exactly right. Thanks. Project Jupyter. No, this is not. .de, I think, right? No. Hub.bbjupyter.de. Yeah, this works. Okay. So then let's take here at the bottom we used this PyTorch Jupyter Hub, I think. And this is what we did last time. And just to see whether it still works, I start it for a moment. It has lost all this thing, but actually we want to do different stuff anyway. So let's try this all together. And as I said, I haven't done it either. So we have to work together. And the first thing we need is to load the MNIST data. And this is a part of PyTorch. So I load Torch. And then I now do my lazy way. So we will liberally use ChatGPT because we are modern. And the thing that I found useful in my ChatGPT thing is, you can give this thing custom prompts. And what I've done here is, let's see if I can show you how this thing works. No, that wasn't it. Here, no. Can't see anymore how to. Anyway, what I've done here is I simply wrote a custom prompt where I told this thing, please, you are my coding assistant. If I ask you something, please answer in one line of code. Don't put all this, import this and that, and assume that I know Python. And then, because otherwise it always first starts with explaining you how to load libraries and so on. So I just told this thing, assume that the user knows Python and just needs a reminder of the things. So, PyTorch, load MNIST dataset as one big tensor. Let's try this. Copy, paste. So obviously we need torch vision. And And now let's see whether this works. Okay, so as you can see, using this thing here, it downloads the whole thing. I wonder how I can do this so that you can easily copy and paste what I have done. Let's take I know what we use. Now, how was this called? hackmd.io. I think this was. There is even now some way that in Jupyter Hub you can collaborative work, that everybody together works on one and the same Jupyter notebook. I have, does this have some kind of sharing link? Open in NB Classic, Advanced Tools, Comment Tools, no. Okay, I do it as follows. Create a note. So, now I can put it as a big QR code. I don't know if this is useful for you to then get it onto your laptop. Yes, you can try that. Nee, ich glaube, man muss den bloß leicht ziehen und dann. I've looked at this before. Here's a sign which says don't pull and use the button. And here next to the button is a sign don't use the button, just pull. Okay, we can, here's this QR code. Maybe, but if you load it with a phone, then you don't get it easily in, but maybe you can just get it from your phone to the other thing. And when you have here, when I will just put all the stuff which I do here, and you can also add stuff here. What? Whoa. Maybe you have to sign in with some random share, publish, maybe a publish node. Okay. Change node permission, copy link. Link copied. Let's try with this one here. QR. Oh, it's still the same one, but try if you can go in now. After I've pressed publish, it's still the same link. Okay, then here. So, everybody got it loaded. So first job, try to find out what we now have in these images and labels tensors. So who has figured out how the data works? What? What does it say? Mm. Local issuer certificate. This sounds annoying because for me it simply worked immediately. I put here train true, download true, shuffle is false. Does it work for everybody else? Okay, and you're also logged in here on this BW Jupyter thing. Weird. And you have a working internet connection. Well, of course, otherwise you wouldn't be logged in there. Maybe try to restart your kernel and make sure that you have used the torch kernel, right? For the others who has figured out how the data works. Yeah. Yeah, the first, exactly. So the first thing I do is to have a look at them and look at their shape. And now I see here, it seems to have 60,000 images with one channel. So it's maybe black and white and 28 by 28. And this is probably 60,000 different images of each of a handwritten ticket. And in labels, we see what handwritten ticket this is. And now let's look at one of these images. I take the images, and now I say I want to take it the image 13 and point 1, comma. Now, how does this work? Image, 0. That's what I wanted. So first I say I take here the image 13, and if I look at this shape, then I get 1, 28, 28. This is not what I want because I have a singlet dimension with 1 here. But if I say 13, 0, then this means take this one single entry which is labeled 0, and now I get something of size 28, 28. And that is this thing here, which has, as we see here, little values, and I can now use, for example, plot.imshow. I think we've used this before. and have a look at this image. And as we can see, this seems to be a 6. We can also look at labels and have a look at the element 13 of labels. No, not plot labels, just labels. And we get, it's a tensor which contains, this is the value 6. And in fact, we see here an image of a handwritten 6. So this is how our data works. We have 60,000 handwritten digits, which, as far as I remember, were made by the US Postal Services when they tried to automatize their zip code reading. So they just photographed letter envelopes and cut out the handwritten images and made these 60,000 handwritten letters. And for each of them, somebody manually annotated which number it is. And now we want to train a computer to do the same. So, and what we can now do is we make a multi-layer perceptron which takes such an image and turns it into something else. That was this plan we made last time that we said, and we will see that this plan is a bit too primitive. We should actually use a convolutional neural network, but let's first try to do it with a normal dense network. So we take our image, 28 by 28, turn it into one long vector of length 28 squared. And then we make some dense layer, which turns this into a smaller vector of maybe, what is 28 squared actually? Just to have a feeling how big this is. 28 squared, 784. And let's make another layer. Yeah, just let's make this one the same size. Or something like 700. And then let's make a layer 50. And then our layer with the 10 digits. And then we check whether we can get this thing to give us a good output here. And that I have no clue whether it works. Yeah. In the labels. You have these images and you have the labels. And if you look at this here, you see here labels at value 13 contains a 6. Have you got it to load by now? Yeah. Okay. So now we can look at how we did this last time with the autoencoder. Where was our autoencoder? Where we made this linear thing here, this thing here, which and I call this now the whole model, because this is not only an encoder. And this encoder starts with the data shape, which is in our case 28 to the squared, because it's a 28 by 28 thing. And then we go from that to a 700 layer, and from the 700 layer to a 50 layer, and from a 50 layer to a 10 layer. And note, this is completely guessing now. I haven't really put much thought into it. And if I now do this model, and I remove the 2 CUDA for the moment, and now I can give this model and give it one of these images here. Images 13.0. But as you see, this doesn't work because it's images 13.0 has shape 28 by 28, but we want it as one long thing here. So instead of this thing, we want it flat. So this is now the shape. And if I want it flat, I have to do something like flatten. And now I get one long layer. And I can now give this here to my model. Point flatten. And as you can see, it now gives me here 10 output values. And later we want to interpret these 10 output values of telling us how much the model thinks that each of that it's a 0, 1, 2, 3, 4 up to 9 here. The first thing we don't want to do is with a single layer. With a single images, we always want to process a few hundred images in one go. So let's try this. Instead of taking here just one, I take all from 0 to 200. Now, let me first see if I can get them that way. Dot shape. And now you see I got 200 of the images. And now I only have to flatten this here, that the 28 by, that this changes from a 200 by 28 by 28 in a 200 by 784. So let's flatten the last two dimensions of a tensor into one. Okay, you see, if I now here were to simply make flatten, then I get the issue that it flattens the whole thing in one very long tensor, but I want it to flatten it only, to keep it, to only flatten the last two dimensions. And this is, as ChatGPT just told me, I can tell it here that it should only flatten the last two dimensions. Now we have 200 vectors, and each vector is one flattened image. And this thing that I now have, I can give to my model. Giving it to the model means it pulls it here through this model, and it gives me out now, for each of the 200 images, it gives me 10 numbers. And let's call this here the output. So let's say this is the input. This here is the model. And this here is the output. Output. It seems input is a special, you see it's green here, so there seems to be a special thing, so I put an underscore behind it because then it's not a special character. So everybody with me so far? And now we have to compare our output with what we actually want. So let's take here, for example, we can take the output of the first for the first image and compare it with the label for the first image. Labels 0. So this here means that it is a 5 and it's so 1, 0, 1, 2, 3, 4, 5. So this value here should be exceptionally high and all the other values should be low. So let's first get this here. Contrast. With -2, the minus always means count from the end. So flatten the last two dimensions. So now we have to think about our correct cross entropy. And I always get this wrong. So let's see if I get it right for the moment. So what we want to do is, ideally, we want something like we get values P0, P1, P2, P5, P6 till P9. These are our values, and this is the correct one. And the others are the wrong ones. So we want this to be high and the others to be low. So in the ideal case, P5 should be high. And so we take log P5 plus sum over all of the which are not 5, and where we add up 1 minus pi. So in the perfect case, the thing would give us 0, 0, 0, 1, 0, 0, 0. In that case, here we would get a 1. Log of 1 is 0, and here we get also 1s. So the best loss that we can have is 0 loss when everything is perfect. And for every other thing, the thing gets smaller. Now for me, to make it easy to write this, I will write it as follows. I will write this now as the sum over all of them. I is 0 to 9. Log 1 minus pi. Now I have to remove the one which I have overcounted. Log 1 minus P5, because I have it here in my sum and I don't want it, plus the correct one. And this is my loss. And we call this a cross entropy loss, because the probability, because we want to add up the log likelihood for the value, and for this we have to calculate, we have to ask what's the likelihood of getting a 5 giving these probability values. And that, of course, to get a 5, this should not happen, this should not happen, this should happen, this should happen, and all these shouldn't happen. This is why we take the product of 1 minus v, because all of those which shouldn't happen, times P5, which is the one which should happen. And then we take the logarithm of this product, and so we get the sum. And we sum up the logarithms of all these probabilities, taking the right one as it is and all the wrong ones as 1 minus as it is. But first we need to get probabilities. And if you look at this here at our output here is, these are not probabilities. And we want to turn them into probabilities. And there is a standard way of doing this, in which this is first to exponentiate them. Now they are all positive, and now I divide by their sum. You see, our network produces arbitrary outputs, anything between minus infinity to plus infinity in this this formula that I've just typed. First makes them all positive by exponentiating them, and then divides by the sum, and afterwards it's a stochastic vector, a probability vector, which is between 0 and 1 and sums up to 1. And this function is called softmax. So instead of typing it as I've done it here, I can also say torch.softmax output 0 and soft for tensor 1 of tensor input in dem null. Yes, exactly. So here you see how the softmax function works. The softmax function does exactly what I've written here. So softmax of a vector x is the element wise of this thing. Now the element I is e to the xi over sum j e to the xj. It's called a softmax because it has an interesting property. If you have a lot of values, of which one value is much larger than the others, Then what this thing will do, it will give you a vector which marks with one high vector with a 1 and all the others with zeros. Let me show this to you. Torch.softmax torch.tensor -3 -3 2, -4. Softmax torch. Isn't this what I've just tried before? Torch softmax output null, none. Maybe it will. Double egg, comma 0. Not implemented for long. 1 -3 dot 2 dot -4 dot. This hasn't worked. Dot transpose. Let me see. Okay, now this is what I wanted to do. You see, I take these numbers, -3, -3, 2, and -4. This number is way bigger than the other. And the softmax marks this now by putting it a 1 there. This is why it's called softmax, because it finds the maximum, but a hard max would put 1 at the exact maximum and 0 everywhere else. And a hard max is a not differentiable function. And the softmax is a softened, smoothened alternative to the maximum, which is differentiable. And so, okay, so this was here what we done. This is our softmax. And as you can see, it gives us here this output, this way of doing telling it that we want the output for every individual value. So have I done this right now? No, 1. Yes, exactly like this. Now with this, it means calculate the softmax over all the rows in the tensor for each image. So I put this here and say this is now props, so the probabilities. And now I want to do this calculation that I've just done, where I say I take the probabilities at the what have I said here? Let's see again. I first sum up 1 minus the probabilities and the log of that. So I take here props x0, that's again for the first one. And I take 1 minus that and take the log of this. Torch.log. And sum this up. Dot sum. And if I did it like this, then I get 1, 2, 3. You see, and now always have to make sure that I calculate this correctly. So these are the values for the 100, but they are all the same. Props, above props, so these are these here, 1 minus props are these here, 8, 9, 8, 8. They are not all the same. They are slightly different because, of course, for the different images, our stuff will give us different. So you see, these are now the values which we get for each image for this. Now, what's the next thing in my formula is minus log 1 minus PS. Now I have to get from my props always the correct label. So I put here labels, input labels. These are now the labels also of 0 to 200. And now I have to find the probabilities for the labels. So the labels are these ones. The props are these ones. And now for each probability, I want to pick out the respective label. And I'm not sure how to do that, so I asked ChatGPT. Given a tensor, 2D tensor, shape n1, n2, with length n1, containing indices between 0 and n2 minus 1. Select the elements. Let's see if it understands what I mean. Because what I now want to do is arrange, yeah, exactly. I show you how this works. I have my probability things, which is a matrix. One row for each image, one column for each of the 10 possible digits. And now in this thing, I now want to select one row each. So torch.arrange 200, props.shape ignored, comma 1. If I do it like this, for example, this thing here will give us this here a range is simply Ctrl V is simply a list from 1 to 200. And if I now put here a 1, then it will select the column number 1 from each row. But I don't want to always select the column number 1. I want to collect the input labels, which tells us which are the correct probabilities. So I have this matrix of probabilities, and from each row I select the one vector element which is indicated by the label. And this, let's call this the good props. And then I have here this sum here, which is, actually I can just take the whole sum over all of them. So this is now this sum already summed over all of them. And now I have to subtract this thing here, minus torch.log 1 minus good props plus torch.log good props. And of course, I have to sum all these up to get my total to get my final loss. So this is my loss. And now one thing I should probably do is that I clamp these things, because the probabilities, they can if they're exactly 0 or exactly 1, then my logarithms here, they will become minus infinity. So I should use here this clamp function, and I keep clamp to clamp tensor. Yes, exactly. And I can tell a minimum and a maximum. So at the moment, the values can be between 0 and 1, but I tell it I want the values to be between 0, 1 and point. Not sure if I made this right. I better write it like this, 1e minus 9 and maximum 1 minus 1e minus 9. So this is my loss. And now I can make a training loop. The training loop works as follows. The same as we've done it here. I copy my training loop from here. I'm really curious whether this will now work. So I make an optimizer, and the optimizer simply contains here the model parameters, like before. And then I go here through the epoch and now give this thing. I've forgotten one more thing. Here I now always give it the first 200 images, which is of course not very useful. So, but let's keep with this for the moment. I put this here because and here I've calculated the calculation from here. Now I calculate here after 100 times going through this, I ask it, calculate the loss. And here you see with the optimizer step as we had it last time. Loss dot backward after they have been freed. So what is my issue now? Input label model dot parameters. Here's the model. And here is this thing now. Images, labels, output. Oops. Okay, where do I do something double? Loss, torch loss. I use the good props here. And the good props, where have I put them? Low, yes. This is why it complains that I do use something twice, because here it uses the one from the previous one. So now you see this takes ages because I haven't moved it to the I haven't moved it yet to the GPU. And as you can also see, it starts with a none. Pretty. Input. So this is how I imagined it should work. Whether it really works like this, who knows? Here we get the loss. Input, input, output model. We first have to make a new model. And then run here the optimizer. Okay, now it works. The first thing is our loss gets minimized. Our loss gets, we said before that the loss should, if we get the perfect solution, the loss should be 0. Otherwise it should be positive, but my loss is negative. So where's my mistake? Is this formula wrong? Let's see, is this formula, does it get positive or negative? This here, for p between 0 and 1, this gives us a negative value, and this is also all negative values. So this should be a negative value, and the smaller the worse. So this is not a loss, because the bigger this value is, the better, because a very negative value means we are very wrong. because this is a likelihood, and the loss is always the negative of a log likelihood. So I simply forgot a minus sign here. And that's why it went in the wrong direction. Stop. So I make my model and I make my optimizer. And now you see it works a bit better. It doesn't immediately crash stupidly. Yeah, okay. All right, we have to switch. So, hey. So this is how far we got now. Maybe let's copy it over quickly to our other thing here, to my hack MD here. So this was the model. What happened? And this here was the training loop. Of course, our training loop is a bit stupid in the sense that it always takes the same 200 values. So what we should do is that we split the whole range of 60,000 things into portions of maybe 1,000 images each and run it on this. So let's see how we do that. We take, we ask ChatGPT, given mute a range n and chop it into pieces of 100 of m elements. See what it suggests now. Chunks is torch random n. Let's see if this works. So of course I don't understand yet exactly how this is. I only have a rough idea. So n is say 1,000 and m is say 100. And if I do this now, chunks, then you see it has now taken all the values from 0 to 999 and split it up into chunks of 100. Each one has 100 things. Now what we really want is that this is as many values as there is images. So images.shape arc0. This should be the 60,000. And here we can ask how many images we do in one go. Let's take these ones. So, and I put this here. And now the next thing I can do is that I now say for E in range chunks dot shape 0. So these are all the chunks. And for each chunk, I can now here say, instead of 0 to 200, I say this should be chunks brackets I. And here too. So you see now it goes through in each epoch, so the outer for loop, each time I go through the outer for loop, I go through all the images, but every time in a new ordering. And if I do this now, it does this, and now it's time to move the whole thing to, you see I'm at none again. Maybe my learning rate is much too big for this. And I haven't made a new model. Ctrl-C. So that it always starts with a fresh model. And now, of course, I want to put the whole thing on the GPU. So what I now do is I move the images to images.cuda and the same with the labels. Like labels.cuda. .cuda always means move this tensor to the graphics card. Do this now. Now this is on the graphics card and the model is on the graphics cards too. Now everything is on the graphics card and you see it now runs much faster. And I can now, what do we now do? Here maybe let's put this here to 100. And see what it does. 100 was probably a bit too many. 100 is 1559. 200. This is our loss. And we did it, and it's simply the loss of the last 1,000 images it has looked at. So maybe this goes down a bit too slowly. I try a higher learning rate by putting this away. And maybe I also change this from 100 to 10 so that I can 10, 20, 30. Okay, this looks quite good, as if it might go down in a reasonable thing. As you can see, usually if you do this properly, you would spend some time thinking about, is this a good architecture? Should I use 3 or 4 layers and so on, try around a lot? But I now just simply try something. And this, of course, is also not good that it always runs out of bounds here. But let's see if here with this learning rate of 0.01, I might get something in the end. 903, 96776, 728. And then the next thing we will try is that once the model has now found in a low enough loss, we will try out whether it does a good job by simply running it on a couple of images and see whether it identifies them correctly. And of course, at the moment, if I will try this with images that were in the training set, which is actually bad style, I should do this with images which are not in the training set. So I should have taken a few images out of this image and label thing, put them aside, trained on all the others, and then see if it can do this. Otherwise, I risk going into overfitting, so it doesn't really understand how to do, recognize digits. It just has learned to recognize the individual pictures. So now you see we seem to get to an area where it doesn't get any better. It always wiggles around 320. 2729, but I don't think we get below, so I stop now. And now I try out whether I got anything useful. So I run my, yes, I just run it here on exactly these images. And can now take here the props, which tells me for each of these 200 images which one is most likely. For example, if I now look at the first one, it seems to be quite sure that it's this one here. You see this 91% of this. So I want to find what is the maximum for a 2D tensor. Get indices of maxima of rows. Argmax dim1, okay. Props dot argmax dim equals 1. So, and now you see this is basically on which indices I had the highest probability. And let's compare this now with the actual labels that we had here, int labels. And 504192113, it seems to have done a good job of recognizing them. And maybe to make sure that we haven't cheated, let's now do it properly with making a proper permutation, and I think I'll do it as follows. You see here I do this random permutation and I remove 1000. So I remove the last 1000 images. So that the permutation always goes only over the first 59,000. The last 1000 the model never sees. Now I restart my training with these here. And in the end, I will take these last 1000 to check how well it has worked. All 10, then it might be that not all of them are on the same device. You see here, I put my model on CUDA here with this one, and I put the images and labels on CUDA here. And you have to do both, because if you load things by default, they're in the normal RAM of your computer, and you have to tell it to push it to CUDA, which means onto the memory of a graphics card. And Torch cannot do calculations with tensors which are, if you try to make a calculation involving two tensors, and one is in the computer's RAM and the other in the graphic card's RAM, that doesn't work. When you started your Jupyter lab, did you scroll all the way down and selected Jupyter for Torch? Exactly, because if you go on this BW services, there's this big thing, Jupyter lab, and that one isn't with Torch. You have to go to scroll, to log out again, scroll at the very bottom and restart it, selecting the one. With what? Instead of Jupyter Lab? No, I'm using Jupyter also from Are you now? Mm-hmm. But you're working on your own computer now. Do you have an NVIDIA graphics card on your computer? Okay, if you have, and that's rather unusual for a laptop, but if you have, then you can install Torch and install CUDA, and then if sometimes with Anaconda it works, but Anaconda properly installs Torch and CUDA. In my experience, this works half of the cases, and usually at least 3 hours of fiddling around with it and trying it over and over until it works. That's precisely why I thought we go to this BW Jupyter. It should work in principle. In practice, last time I tried it, it took me 3 hours. In the end, it got it to work, but yeah. So let's put together what we now have here in my hackMD. Here we put this one here, and here this is now the CUDA one. Yeah, this thing. Oh, you see, I let it run too long, and in the end it ran into none. So let's start it again, and let's do only 1500 epochs. 1500. Stop it, start again. So, while this starts again, we can think about why this is actually a little bit stupid what we are doing here. You remember, we connect each pixel here via the dense network with all the pixels here. And each pixel gets interpreted differently by the neural network. So if we have 2 6s and one is written like this, in Java is written like this, exactly the same shape, but only shifted a little bit to the right. This network won't recognize it. It will have to learn this separately from that. There's two ways to get around that. One is called data augmentation. We simply, for every individual image which we do, we not only feed the network in training with this image, but also with the same images shifted 1, 2, 3, 4, 5 pixels to the right, to the left, to the up, to the down. But that, of course, increases training numbers a lot. And the other way is to make the network itself shift invariant. And that works with convolutional networks. So you see here at the moment, we have this idea that to get from here to here, what we do is that this layer, let's call this here Z and this here X. And the way how this works is that we say Z is some matrix AX plus some bias vector, right? Maybe I should switch on the light for this again. And in writing this out in, and of course, our ReLU activation function. Writing this out in components, we can say Zi is the sum over J, Aij, Xj plus Bi. This is simply the matrix vector multiplication written out in components. The next thing I can do is I could now, if I want to use my X as a 2D thing, because after all it's an image, it has rows and columns. Instead of having one index J, which goes from 1 to 748, I have two indices, J and K, which both go from 1 to 28. And I write this thing here is Aijk plus Bi Zi equals JK. So you see what I've done? It's still the same thing, but here I have rearranged this matrix. This is a matrix of shapes 700 times 748, and this is a matrix of a tensor of shape 700 times 28 times 28. But it's still the same calculation. I only changed the shape of it. And that's the reason why people call it tensors, because it's so easy to change the shape. And then we just have to change this single sum, which runs from 1 to 728, to this double sum, where each index runs from 1 to 28, and it's still the same thing. So that's one useful thing. That's just a rearrangement of a thing. And now I do this new thing where I say that I equals No, let's do it the different way. I can also do, of course, make the second level also two-dimensional and make something like Zij is KL, Aijkl, XKL plus Bij. How does this now work? Now I have a four-dimensional tensor. Element Ijkl means we have an input image, 28 by 28, and we have an output image, maybe also 20 by 20 or whatever. And this value here tells us how strong the output pixel Ij is influenced by the input pixel KL. And in a way, this is still the same as before. I only changed my indices, that instead of having one long index which goes through the whole vector, I just use squares. So I say I turn one square of 28 by 28, maybe another square of 20 by 20. And for this, I have here this thing runs through all the levels of the first image to get a pixel of a second image. Everybody with me still? And now comes the trick. This last thing I now rewrite as follows. Zij is, hope I get this right immediately, A I J K L K, L gleich minus 3 to 3 X I plus K, J plus L. So how does this now work? What now happens is I have made a convolution. Basically, I'm saying that I have here my input image and here my output image, which might be a bit smaller. And this pixel in the output image is calculated from, say, these 9 pixels in the input image. Which means this pixel is a linear combination of its left neighbor, its upper neighbor, its right neighbor, and so on, of all its neighbors. Here I've drawn it with neighbors up to distance 1. Here I've drawn it with neighbors up to distance 3. So you see here we inspect the input image at all the pixels from 3 to the left of the output pixel up to 3 to the right. And we say from 3 below to 3 to above. So we have overall, we take this pixel here depends on a total of 49 pixels, because this runs from minus 3 to 3, that's 7 values. And so this here runs, so this double sum runs over 49 values, and these are the 49 pixels which form a 7 by 7 square around the input pixel. And in that case, this thing here, this output pixel depends on these input pixels, and that output pixel might depend on these input pixels. So everything depends on its neighbors. And the way it depends of is given by this tensor, and the tensor is always the same. So every output pixel depends by one specific thing on its upper left pixel and on its lower left pixel and so on. And that is the trick. So when you now move the whole thing a bit to the right, then this thing will also look the same, only moved a little bit to the right. And in practice, you may build the network such that you go in with your image, and then you use such a convolution thing to turn it into another image, which is typically a little bit smaller, because you see, you always need, because you see this box here, it has to fit, so we cannot process the borders. So this means it makes it a bit smaller, and we get one matrix A which produces this, and a second matrix A2 which produces a second, and a third matrix which produces a third one. And then in that manner, the model can learn to look at, to notice different things. For example, if the matrix A looks as following: minus 1, minus 1, minus 1, 1, 1, 1, minus 1, minus 1, minus 1. Then if we have a pixel, which sits within a vertical line, then we will get this and this white times minus 1, white times minus 1, and black times 1. This gives you a rather large value. While if we use the same kernel on a horizontal line, then we get 0, because this point here gets here minus, 2. Because if you multiply this pixel now with that thing, then its new thing will be the average of minus 1 times this, plus 2 times this, minus 1 this, and because these are all three the same, it's simply minus 1 plus 2 minus 1. That means it gives 0. So this thing here, if you make this convolution product, and this thing that I've written here is called a matrix convolution. if I make this convolution of this thing with that pixel, I get again a line. And if I make a convolution of this thing with that thing, I get zeros. So this thing here, we call it a kernel. This is a vertical line detector. While this here is a horizontal line detector. And you can come up with different detectors which detect different things, kinds of things. But we don't have to come up with them ourselves. Our network will learn different kernels. And for each kernel, it will, learn how, and what we do in a convolutional network is we go on with our image, and when we tell the network, produce several, for the next layer, produce several slightly smaller images, each image coming out of convolution with a different kernel, and then try to learn kernels which are helpful to detect image, to classify the images. And because this thing is translation invariant, if you change the image, input image translated, then the output images will also just be translated. It is much more efficient at learning how to identify things on images than if you just do this dense network. And these so-called convolution layers, that was one of the first big ideas which got this whole image analysis and detecting images going. There were a couple of later things, but essentially, for example, this network of George Hinton, for which he then later got the Nobel Prize, it was essentially stacking, I think, 80 such convolution layers behind each other. Yeah. Trial and error. So in practice, and the nice thing with PyTorch, if I now wanted to change, which is terribly simple, I just have to replace the word linear here with convolutional 2D, and the rest goes all by itself. And I think for convolutional 2D, you have to tell it the size of a kernel, whether it's something like here, 7 by 7, and how many different kernels it should learn. And then you can go through the whole thing like that. But what I wanted to do today is to show you how to make the most primitive possible classifier using just dense networks, and point out, of course, that these dense networks are an overly primitive thing, but for something as simple as classifying handwritten digits, it works. So let's see whether it works. You remember before we had just told it to run through here, but I again ran into nonce. So one last try, just make 500. So I run through with 500 networks. And then, okay, while it does this, I can already think about how I will get the final ones. So I have to take images, but not the first 200, but the last 1,000. So I think I simply can say minus 1,000 to 0. Yes, exactly. So I replace this here with minus 1,000 to 0, and this also with minus 1,000 to 0. And with that 200, and I think this won't get any lower. I stop here and try it out. Input images. Good props. So here you see these are the things 685721, and these are the actual labels. Let's see how often they agree. Would not infer output D type. Okay. Some. Okay, 958 of 1,000 digits were correctly identified. It would now be even more impressive if we would now write a little thing that we write a digit with our finger. I've just found out, you know, I bought this computer used just a few days ago, and I've just noticed only 5 minutes ago that I seem to have a touch screen. So I could now draw with my finger a 6 on it and put it in our bring it down to 28 by 28 and put it into our classifier and see if it can also read my handwriting. It would in principle be no big thing. Probably the difficult part is now I would have to find out how to use my new touchscreen and how I draw something, and then how I rasterize this down to 28 by 28 with Photoshop or whatever I want to use, and then how I get translate this 28 by 28 matrix, how I move it here on this server and put it in. But you can imagine that in principle it should work. So what we have now done is we have solved the problem of the US Postal Service of automatically reading this postcode by looking at handwritten digits and with 95% precision to identify the digits correctly. 95% is probably not good enough for the Postal Service, but I think it's quite decent for us just having spent an hour on it. And I think this is a very nice example because you can see how we really built the whole thing from scratch. Just coming up with some more or less randomly made up network, just 3 linear layers with some sizes which I simply pulled out of thin air. When this simple training loop, which always takes 1,000 images and runs them through the networks, and this simple loss, which simply checks these things. So what we needed was this softmax idea. We needed this specific way of writing to loss, which is called a cross entropy, in case you want to look up the exact mathematical justification that you can write it like this. And when we just used PyTorch's magic auto differentiation, which automatically calculated the derivative with chain rule of this complicated loss with all its logarithms and 1 minus and so on, and all these matrix vector products and so on. And in this, it could find the derivative of our loss with respect to each of the elements of these 3 matrices with its 3 basis vectors. And that worked, more or less. I mean, it's a bit unnice that we had to stop it in time before it became all none, because the minimization somehow overshot and suddenly it didn't work anymore. But these are all details which you have to even out if you want to build something which is reliable and robust and works in practice. But just to experiment to see whether we have understood the principle, this is an easy way. So this was now basically the standard textbook example of machine learning. If you do any kind of machine learning course, this is usually always the advanced example number 3, write a classifier for the MNIST digit example. And originally, this was a very complicated thing. I mean, the US Postal Service put lots of millions of dollars into this. And the reason that we now solved it and we now could train a thing within 2 minutes instead of spending many months is, of course, because nowadays computers are simply by many orders of magnitudes faster than when they first tried this 50 years ago. And so we could even get away with our non-translation invariant, rather clumsy multi-layer perceptron. And I told you in the lecture how they built a 1-layer perceptron already in the 1960s, and were terribly disappointed that it didn't work at all. Now we just increased it from 1 layer to 3 layers, and it works beautifully. And they would have, but back then that was simply out of the scope of what you could do. So, any questions, remarks, other stuff to that? Where's 50? Why 50, you mean? I just pulled a number out of random thin air. So my idea was I wanted to make 3 layers. I thought let's keep the first layer simply on the same scale. We had 728 input things, so it should also be around 700. The last layer, of course, has to be 10 because we have 10 digits. So the middle layer should be some number which is smaller than 700 and bigger than 10. Could be anything, but I thought 50 is nicely in the middle. Between 10 and 700, at least on a logarithmic scale, it's sort of in the middle. In practice, of course, this is what we call hyperparameter tuning, where you then spend a couple of days trying out different things. Should we make 4 layers or 3 layers or maybe 5? Should we use bigger or smaller layers? Where are here? Because the whole thing initially, our input tensor is input.shape. Our input, no, how would I call it? In images. So the images is a tensor of 60,000 times 1 times 28 times 28. If I now say flatten, let's keep it like this below. If I now say images.flatten, dims is -2. Was it? No, last dims, right? Start dim. When this means -2 means the second to last dimension, start with there, so take these 2 dimensions, the 2 28s, and make them into one 748, so that we then get this here. And this then means that every image is now one vector, and hence we can easily push it into into our perceptron because it wants a vector as input. Yeah, exactly. Flatten simply means take the final dimensions, and you have to tell it whether it's the last 2 or the last 3 or whatsoever. Yeah. This was here. So I took the same code that here was my code, and you remember this was the code we used to run the model. I copy and pasted this code down here. Same code again, but this time I used these images, the last 1000. Flattened the input as before, ran it through the model, got the output, made my softmax, calculate the good probabilities. No, I don't even need them. This here. And now I ask for the probabilities, which is now, remember, above props dot shape, 1000 by 10. And if it's 1000 by 10, each individual means each of the 1000 rows is the probability output for one image. And this image, I hope that typically, so let's look at one of them, you see, typically all these values are quite small, except for that one. This is much higher than the others. All the others are below 0.1, and this is 0.98. So in every row, there should be one maximum, and I try to find out where these maximums sit here with this thing, which means in the dimension 1, so the rows, always find out at which index is the maximum value. And this should be, of course, the index of a corresponding digit. And this is why down here, I compared this simply with the input labels and ask how often do they agree. More questions? Mm-hmm. It's weird that it runs out of memory for you if you're on the same machine as me, unless we just happen to be on the same machine, and now with 10 people it's not enough. So yeah, you could try it again later, and when you maybe have a machine all for yourself, because you're sharing it effectively. The other thing is, of course, what we've done here is we move all 60,000 images onto the graphics card. In practice, you wouldn't do this if you have lots of training data. Rather, in your training data, you would leave images on the CPU, take the chunk of images you want, and only move this part onto CUDA. So I would put the CUDA not here for all of the images, but what I would put it here after the subsetting of the images that I want to use for the current training iteration. And then, of course, I need much less space. In practice, it's actually usually you try to make optimal use of your GPU, decide to make the chunk size just so big that you fully use your GPU. Other things? Otherwise, if you have other questions, just ask me. I now have to run, actually, I guess. Yes, because in 15 minutes is the bus up to Emble, and I need to go to Emble now. So I go there, and I hope that was now of interest